Hello, parametric functions right here. This is Calculus BC, or second year calculus material, and this is just simple differentiation of parametric functions, as they're commonly called, conversationally called that. Just quickly getting into it, how to use it. And so, as a reminder, which you might not be 100% familiar with parametric functions, just the non-calculus aspect of it, but just I forgot what a parametric function was, or what makes it different than a normal function, a non-parametric function. That's not the point of this video, or any of the videos, for that matter, that are here in the Calculus BC, our second year calculus section. My goal is to just actually talk about derivatives and integrals of the parametric functions. So you have to look at learn about that somewhere else, or if I have a video up about regular parametric functions, which at the moment I don't, but if I do, then obviously you can look at that and learn about them. But given your x equals f of t and y equals g of t components of the parametric function there, you get to find your derivatives, which this is interesting. So define the first derivative, right? That's what dy dx is, the first derivative, as you know. It's this interesting looking expression, dy dt, dx dt. There's a fraction here. This is a legit fraction. We always talk about how the differential is not a fraction. The dy dt is not a fraction, but this here, the red black line here, that actually is a fraction. So, and speaking of them not being fractions, the differentials, these things, the lines there, it's interesting. We also say though that you can almost treat them as if they are fractions. You talk about that, and that once again applies here. I mean, if you think about it, if you have a dy dt over dx dt, if you had something like that, you could write this as a product, right? You could write this as dy dt times the reciprocal, right? The reciprocal, so it would be dt dx, and then get dy dx. Oh, which is the derivative, which is what we started off with. Hey, so once again in this instance, you can think of the differential as kind of a fraction. That's why this relationship is true. But as we always say, as math teachers say, and as I say, they're actually not. These are not fractions, and it's kind of important to be aware of that. But in some instances, like this one, you can treat them as if they are fractions in a way. And then you have the second derivative here, and this is the way we compute the second derivative for parametric functions. And so the numerator there, you're taking the derivative with respect to t of the derivative of y with respect to x. So these are the ways we do the first and second derivatives. Of course, this means that your answers will be in terms of t, right? Your derivative functions will be in terms of t. So perhaps that's not desirable, which is possible. I mean, since this is dy dx, right? It means it's a possibility that perhaps you'd be asked to find dy dx in terms of y and x, not in terms of t. Or in terms of just x, dy dx in terms of just x, right? Sometimes you'll be asked to do that, and in that case, what that would mean is you would have to change the parametric function and convert it into a regular non-parametric function, which you can do by just simply setting since each x and the x equals and the y equals each have t's here. Since they each have t's, you can just set them equal and combine the two equations there. And so you can convert it into a regular non-parametric form, and then just take the derivative like you would of any normal function, and then that's how you can find the derivative without having t involved in your derivative function. Anyway, so there you go. That's the intro, and we're going to have some fun doing first this example problem, and then some later ones in some of the future videos. Stay tuned.